gears to look at air-sea fluxes. So we've been using wind to drive the ocean, arguing that it doesn't drive the ocean. But now we actually want to look at what is fluxing energy between the ocean and atmosphere. And I want to start by just asking you to look at the figure here. So we're looking at net heat flux from 2008 to 2017. Take a moment. What do you notice? Yeah? Yeah, so just for context, this is mean is heat flux. It's in watts per meter squared. And yeah, there's a band of really high heat flux. There are 3 panels here. What about them? Yeah, so that's one of our challenges. We've got 3 products here, pretty reasonable products. These are major reanalysis products. And in many ways they agree, but there are striking differences. And that's sort of our warning that there's a lot we'd like to know that clearly we don't agree on. We have work to do. And so that's a context for what I'm going to talk about. I thought, just to get started though, I thought I should, since everybody else has talked about how they got here, I thought I'd give you a little context for myself. I grew up in Boulder, Colorado, so I spent a lot of time well above sea level, looking at the tipped remains of ancient seas, and really thinking about how I might be able to contribute to big environmental questions. I studied physics as an undergraduate, and I was fortunate to get summer jobs at NCAR. I worked with acid rain modelers and other people, but I started thinking what was the problem I really wanted to work on, and I was fortunate eventually to end up as a summer student at Woods Hole, where I got involved in amazingly looking at satellite data in an observationally oriented organization, and really and I thought this is something where there are really great problems and I can get involved in this. And then I had graduated from college. I was not ready to face grad school, but I persuaded some people in a lab outside France in a place called Verrières-le-Buisson to hire me. I worked on diurnal variability in LIDAR data in the atmosphere, atmospheric tides, and learned a lot, gave myself some space to figure out where I wanted to go, and I applied to grad school and ended up, same photo that David showed at MIT Hui in the MIT Hui joint program, where I worked with Kathy Kelly on satellite data. Kathy had been looking at the Gulf Stream, and she said, you know, somebody should really take some of these ideas that we've applied to western boundary currents and look at the Southern Ocean. So I did that, and I have kept going on the Southern Ocean ever since. So, and so I finished my degree eventually and ended up as a postdoc at Scripps. This is a photo you can't quite see, but it is the Scripps Pier shot with the setting sun through it just a couple days ago. So it's interesting to be somebody who works with satellite data and autonomous data at an institution that is decidedly seagoing. And it gives me great perspective. I'm sometimes bucking the trends anyway. But so I'm happy to talk more, but I really wanted to look at questions about how energy gets into the ocean. We left off yesterday, and I talked about heat content or heat input to the ocean, and the fact that when we look at how much energy is in the ocean and how it's changing, the rise in ocean heat content, and this is from an analysis of a whole bunch of different products in situ and reanalyses, but all agreeing with, this is global, but these are numbers that are consistent with what I showed you for the Southern Ocean before, that there is sort of a 0.6 to 0.7 watt per meter squared net input to the ocean on a global scale. So that's telling us that there's a big heat flux to the ocean. It tells us that one thing. There is so much it doesn't tell us, and that's where we want to head today. So we looked at water mass transformation, what put energy into the ocean, the sort of question of what fills the reservoir of heat. But today I really want to talk about air-sea fluxes. So I'm going to talk a little about foundations, heat fluxes, momentum exchange. I'll talk a bit about the specifics of the challenges of obtaining Southern Ocean air-sea fluxes. And then I'm going to talk in a little detail about the in situ observing system, what we might do to improve our array. There are people here who are way more expert in this than I am. And about some of the opportunities for doing things from satellite, which will take us straying out of the Southern Ocean. But obviously, the Southern Ocean is such a big part of the ocean that this is important. So I have this figure here showing many of the processes we're looking at. But what I really want to emphasize, I'm going to talk about air-sea fluxes, but that's sort of just a shorthand or maybe a misrepresentation of what really matters, because this is really something that depends on what's often referred to as the air-sea transition zone. The flux is happening right at that surface layer between ocean and atmosphere, but it is so intricately tied to the marine atmospheric boundary layer and the ocean boundary layer, the mixed layer, that we really need to think of the whole thing as a continuum. And there's been a big effort from this air-sea transition zone to articulate what needs to be done to look across the entire transition zone. So here's the crux of the problem. Anything we look at, this is for fluxes, but any aspect of the ocean system we look at has this really broad range of scales. So we can look at anthropogenic warming. It happens over very long time scales and very large spatial scales. And that's where our measurements from Argo that say, look, the total integrated heat in the ocean has increased, are doing a great job. But all of that warming is happening because of a lot of processes that happen over smaller spatial and temporal scales. Things like turbulence in the marine atmospheric boundary layer, or air-sea interactions on the shelf. And so there's this continuum of scales, and these things happen at much smaller spatial scales and much smaller temporal scales. And they are definitely not resolved by Argo floats profiling every 10 days. And so if we're doing a great job with this stuff, we have a lot of work to do to figure out the mechanisms that drive this sort of change through processes that happen at these scales. And that's why we want to be able to measure fluxes. If we just needed to know what was happening on the anthropogenic scales, we would say Argo is going to solve everything, and we're wasting our time if we want to look at the air-sea fluxes, because we will never be able to measure air-sea fluxes at point measurements to get the numbers that explain this anthropogenic change. But we'll never understand why this is happening unless we make measurements at the small scale. So that's my prelude. So we're going to talk about, there are a whole bunch of ways that the ocean talks to the atmosphere. This involves heat exchange. It involves wind current interactions and gas exchange. I'm not really going to talk about gas exchange, but I'm just laying this out because I do want to get through this full scope of processes that let the atmosphere and ocean talk to each other. These are the processes that really matter to explain our climate system. So I'm going to start with some of the basics. Air-sea fluxes is exchange of momentum, heat, and mass. Momentum flux is essentially wind stress. Heat flux has 4 components. So there's shortwave energy, that is the energy from the sun. There's long wave, which is the black body radiation from clouds and the atmosphere going into the ocean and the ocean re-radiating out into space. That's what's plotted here. So we have shortwave, this is for July. So shortwave downwelling flux is in red. The long wave downwelling is in blue. There should be a long wave upwelling as well. And you can see that these are in the realm of hundreds of watts per meter squared. They are big numbers. They have big seasonal cycles. And then there are sensible heat fluxes and latent heat fluxes, which I'll come to in a moment. And there's gas exchange. All of these components, these other components, not the shortwave and long wave, but everything else gets classified as a turbulent heat flux. It depends on a covariance between 2 quantities, wind and something else. And these are not easy to measure. So we typically rely on bulk formula to make flux estimates, but the bulk formula are best guesses at how to parameterize something, and they're probably wrong in interesting and complicated and difficult ways that require way more observations and flux systems that we don't have. But we can just track through these. Momentum flux, that's wind stress, depends on density of air, drag coefficient, it's plotted down here, not a constant, and this S sub r, which is wind stress. And it was written this way because it's not just the wind speed, it's the wind speed relative to the ocean currents. And I'll come to that in a moment. Sensible heat flux, so that depends on the air-sea temperature difference, delta theta, and this wind speed that's not wind speed, it's wind speed relative to ocean currents, and plus a whole bunch of coefficients. Again, there's a constant in this that is not a constant. And latent heat flux is depending on the humidity difference across the air-sea interface. That sounds a little weird. I think the ocean is pretty humid, but it again depends on wind speed and humidity difference. And so all of these are written this way. This is a bulk parameterization. There is a whole lot of other stuff going on that is not necessarily represented here. And then gas flux I put in here as well. That's really similar sort of formulation. The gas flux depends on a coefficient, difference in partial pressures of gas concentrations, and wind speed. So if we want to measure these things, we like to have observations. And so this is a map of available observations in the Southern Ocean. This is for July, so maybe not the best month for getting in situ observations. The dots show all of the measurements available for July for a 5-year period, 2000 to 2004. And you can see that there are places that are reasonably well sampled in July. They aren't really in the core of the ACC, maybe not really in the Southern Ocean. So we've got a lot of gaps in our observing system, and that's a real challenge. There are 2 moorings shown here. I don't think either of them was really active in the 2000 to 2004 range, but they got plotted on the same plot. So the big black circle is the Australian soft mooring. It's an excellent continued record, just redeployed. We have lots of expertise here. And so that's been a good continuous record. The star is a mooring that was out from the U.S. National Science Foundation's Ocean Observatories Initiative, and it was out for as long as anybody could persuade it to be out, which was not very long, a few years. It stayed longer than it was supposed to because they had trouble with the recovery, and so it got left in an extra year. That was a victory. But really, we have this great dearth in observations, and so that leads us to think, what are we going to do? How do we actually measure the processes that are driving air-sea flux? And just to give you context, what we really want to know, so this is trying to make hay with the few observations that are available. So this is an analysis that Veronica Tamsett led, comparing the SOFS mooring and the OOI mooring. So they're superimposed here. You can see the heat fluxes from these moorings for the time periods when they overlap. So it's sort of 2015, 16, 17, and 18. The annual cycles are pretty similar in these 2 moorings. They show really similar sorts of records. So if you just look at them in a very broad brush sense, they're measuring the same thing, and we don't have anything to worry about. But what you need to do is look closely at what's going on, because the fine scale data are showing these really extreme events. The massive cooling or heat loss events are happening as very short-lived episodic events. That's what's really driving all of the stuff that's interesting at these locations. So everything that leads to deepening the mixed layer, sequestering heat into the ocean interior, is happening because of one single storm event over the course of an entire year that is bringing cold air off the Antarctic continent and leading to massive heat loss at the surface, leading to a deepening of the mixed layer and a whole lot of stuff happening all at once. And then the whole system goes back and nothing much happens for a while. And so it looks like if you really want to understand how the ocean sequesters heat or CO2, if you want to understand what processes are driving it, we need to actually measure these really short-lived episodic events, which is hard to do if you're measuring by having a ship out for 2 weeks in July, or in maybe never in July, maybe in January, or if you have Argo floats or other instruments that are out just for short periods of time or that profile infrequently. And so we have this question, what do we do? The other question is, we're really talking about things that depend on extreme events, extreme winds, and we have a very poor picture of what that looks like at the moment. This is a plot showing, this is from Momay Hell's thesis work, and it shows probability density functions superimposed for the zonal component of wind and the meridional component of wind in the Southern Ocean. It looks at 4 different products. So there are ERA5 is a reanalysis. There's the European scatterometer product in a green line, and those pretty much agree. But then there's a separate analysis. CCMP is a compendium product that puts together scatterometer winds, so satellite winds, and with an initial prediction from, I think, ERA5. That's the blue line. And you can see it's got, they agree in the core, but it's got a really different set of extremes. It's very different in the tails of the distribution. And the remote sensing systems analysis of the same scatterometer winds also has this different set of extremes. And so we've got these outlier events, things that are the one strong wind event that might be deepening the mixed layer or not deepening the mixed layer. And they're completely different depending on whose product you're looking at. And so how do we reconcile this? What do we do to get through this? So that implies that we actually would like to have more extensive observations, a better understanding of this, a better understanding of how to evaluate our scatterometer winds. And I want to emphasize then, part of what matters is also that we're not just measuring wind, we need to measure wind relative to currents. And this is illustrated here. We've got an eddy, like the eddies that David was talking about, and we've got a large-scale wind blowing over the eddies. So this is these orangish vectors here. So you can imagine, if you have a uniform wind blowing over the eddy, on the north side of the eddy, the wind is blowing against the surface current. And so that means that the wind is super strong relative to the current because they're going in opposite directions. And so that gives you an extra strong wind stress, which is counter to the surface current. It's going to slow it down. On the south side of the eddy, you have the wind blowing in the same direction as the surface current. So now you've got the wind and the current moving in the same direction. That reduces the effective wind speed relative to the current. So you have a weaker wind stress, so it's putting less energy into the eddy. And so both of these tend to weaken the eddy. It's referred to as an eddy killing effect. Maybe eddy killing is a little too strong. It's slightly suppressing the eddy. And this is an interesting phenomenon. If we only measured the ocean from satellite, we would have nothing to worry about. Satellites always are measuring surface capillary waves that depend on wind relative to currents. They always measure relative wind. So if we only had satellite data, we'd have relative wind and we'd have this fully under control. The problem is that we have to calibrate our satellites with in situ measurements. And our in situ measurements are from anemometers that don't necessarily measure relative wind. Oops, so advanced. If we're going to look at, if we're really going to understand how the wind is driving the ocean, we have to keep this relative wind effect into in mind, it has a big impact. This is looking from model results at the effect of including relative wind. So here's an assessment from observations from this study by Hyode So. This is looking at the model with the relative wind. So the wind is taking account of the surface currents. And you get a mean wind work, in this case in the Agulhas region, of about minus 0.33, whatever the units are. If you run the same model and have no relative wind, so the wind is unaware of the surface currents, you get a different sign, positive 0.1. The difference between them is bigger than anything. So it really matters if you're going to figure out how much momentum is getting pushed into the ocean. It really depends on understanding the wind relative to the currents. And most modern models take this into account if they're in any way coupled. This also has a big impact on heat flux. So this is looking at the net heat flux in the model with relative wind and the difference between relative wind and no relative wind. And you can see there's quite a big difference. This is in the sort of 50 to 100 watts per meter squared. So the paper that studies this, Hyode's paper, says mechanical and thermal air-sea interactions are inherently and inextricably linked together. They say over the Agulhas retroflexion, but that's only because they only studied the Agulhas retroflexion. It's everywhere. If we're going to understand the heat flux and the momentum flux, we do need to take this into account. And so we have this system, this case where we really know that we want to be able to measure this stuff. We have a shortage of observations, and there's been a big effort really arising out of OceanObs 19, the community effort to define how we should observe the global ocean, to identify there's an enormous concern about air-sea interaction. And so from that grew this effort called OASIS, Observing Air-Sea Interaction Strategy, which has been a global effort. Megan Cronin and Seb have been co-leads, along with Krista Marandino. So OASIS has articulated a set of grand ideas, and they're laid out here in this diagram, which groups them along with the various white papers, community papers that articulated these as part of the OceanObs effort. But grand idea number one is that we actually need a globally distributed in-situ air-sea observing network. Part of that is, if you talk about globally, and the Southern Ocean is the big part of the global ocean. A lot of this is about dealing with our gaps and getting into the Southern Ocean. So grand idea number two says we need satellites to pull that together. And so I'm going to talk about both of those. And then grand idea number three says, well, we should improve models and understanding and make sure that we're serving stakeholders around the world. So it's really articulating a very strong vision for where we should go. I'm going to start by talking a little about grand idea number one and how we can deal with surface observations, and then I'll talk a little more about satellites. So if you want to directly measure fluxes from in the ocean, and then you're talking about putting out moorings with flux covariance systems, with anemometers, or using autonomous systems like sail drones or wave gliders to try and get at measuring upper ocean variables. And the question then is, how should we set up our observing? And so one question that has arisen is, suppose we did have funding to put out more measurements in the Southern Ocean, where should we put them? And this question is almost not an idle question. The Southern Ocean Observing System was approached by Dake Chen, who had recently moved back to China, and he had a notion that he could persuade the Chinese government to fund the big ring. This was a notion that it would be possible to put maybe 8 moorings around the Southern Ocean. And he said, well, where should we put them? What's the ideal place to put those moorings? And so that question was posed, and a subgroup of SOOS, the Southern Ocean Flux Working Group, which Seb and I were co-chairing at the time, was asked this question, and we said, you probably could do a little investigation and articulate where to put moorings. So this is really predicated on the notion that if you want to have in situ observations to do process studies and to reference satellite observations, then there are a whole bunch of metrics you can use. But let's think about a strategy for maximizing what we can do from a set of moorings. So one strategy is to try and explain as much of the variability as possible in the system. And so a postdoc was persuaded to work on this way. And so here we're looking at the mean fluxes in the Southern Ocean from the JRA product and the standard deviation. And the question was just, suppose you want to explain as much variability as possible. So first we have to decide what we're really trying to do. And there are a whole bunch of time scales in the data. There's a really strong annual cycle. And so so he said, well, probably you don't need to explain the annual cycle. So we can take that out. We can look at variability. And you can imagine looking at variability as either high frequency or low frequency variability. In this case, the focus of the analysis was on high frequency variability. But that's sort of a fudge because this is looking at monthly fields. So we're looking at sort of high frequency variability, but not every single storm. So we've got this blue line, which is the high frequency variability, not the annual cycle, but not the daily scale. And we're going to say how can we maximize the variability explained by that? So maybe this isn't the final answer in the end. It's going to be a proof of concept. So if we have the high frequency variability, we've got the heat flux, buoyancy flux, difference between them. They're just different ways of articulating the same thing. And then we can go through and say, okay, suppose we want to explain the maximum variability possible. So we can look at the standard deviation of the data, and you can say, where would you put one mooring in the Southern Ocean if we had to explain the maximum possible variance? So what place is best correlated with everywhere else? And that turns out to be this black dot here. So you can see there's quite a bit of variability. You can look at the correlation between that. So we're going to take that as the target location. Here's a place to put a mooring that will explain as much heat flux as possible. Then once you put that mooring in place, then you can say, artificially, using data, using the reanalysis fields, if we've explained that much variability, where should we put the next mooring? And you repeat this process iteratively. So we have mooring number 1 goes there, mooring number 2 goes here. That's not too far away, but also a place of a lot of variability. And explains more variability. And so we can go through and get a whole set of moorings. Here are 6 moorings positioned around the Southern Ocean, each of them explaining a lot of variability near the location of the mooring. And this then sets up the whole array. So we've got them numbered red, blue, black, and purple. It's worth noting that position number 2, this red star, is pretty much the same location as this defunct Ocean Observatories Initiative Southern Ocean mooring. So it was a pretty good location to put a mooring. Would be a good place to put it back. And it's also worth noting that if we were trying to get synoptic weather scales, higher frequencies, we'd do something different. And so this is not necessarily the final answer, but it's a way of looking at this. This study goes through and looks at a whole bunch of other cases. Oops. What have I done? There we go. So we can look at the base case. So you could just put them south of 40 south. You can weight the fields differently. You can assume that OOI and the soft mooring already exist. You can use a different heat flux. So all of those subtly change them and end up with fairly similar types of distributions. And then finally, you can say, okay, we've got this set of moorings. Here's how much we can actually reconstruct from the field. So we're doing a good job near the moorings, not so well everywhere else. And here's the difference between the total heat flux and what we reconstructed. And obviously, we've missed a lot. Here the black dots show the next 2 places to put them. So in total, we're getting 24% 24.6% of the variance. We are nowhere near, with this mooring array that is vastly larger than what's currently out in the Southern Ocean, we're coming nowhere near explaining all the variability, even on sort of monthly timescales. And so that's an important point. We're not expecting that we'd see all of the Southern Ocean fluxes. We think the reanalyses will help with some of that. But we are getting this hypothetical array would give us a much better view of individual events and what's happening. And this is this 24.6% variance is pretty good. It's noted here that if you went through and just took the first 8 empirical orthogonal functions, you'd get 36.6% of the variance. So this is not an easy system to explain compactly. So just to summarize all this quickly, we've got this framework. 8 moorings explain 24.6. If we'd done the low-pass heat flux variance, we would have explained 44.7%. And that leaves these open questions. How do we optimize flux measurements across the features that we aren't explaining here? Narrow frontal features, how can sail drones and wave gliders help? And so there's a lot more that could be done. So this is the challenge. If we really want to understand processes, we probably need a much expanded flux measurement system, including an array of things that none of which are funded at the moment. And so with that, I'm just going to turn to the other end of this, which is grand idea number 2, and ask what we can do with satellites. So satellites give us a really different way of looking at the ocean. They sample typically on a sun-synchronous orbit. This is showing, so this is a plot that appears on the World Met Office website. It is showing wind satellites across from all countries in the world that put up wind satellites, with a timeline showing what's supposed to launch in the future, so from 2024 moving forward. What is important to notice here is that most of these are labeled as sun-sync. That means they're sun-synchronous. They measure on an orbit where they measure at 2 times a day. And the times a day are shown here. So typically, many of them are measuring at 9:30 in the morning and 9:30 at night, local time. Some are at 6 a.m., 6 p.m. There is an enormous gap in the sort of 3 a.m., 3 p.m. range. So we don't do a very good job measuring them. They're also distributed over a range of countries. So many of these are Chinese, HY and FY, and data access has been challenging in some places. But the other thing to notice is that as we move forward, there's a lot happening in the next few years. There are big gaps as you get beyond 2030. So we have a lot of uncertainty about what the future will bring. So wind, in any case, we need to do any measurement of air sea fluxes. Every single flux variable depends on wind, and so this is a fundamental quantity. If we want to look at heat fluxes, we need sea surface temperature. And there is one good thing coming along, which is that SIMR, the Copernicus Imaging Microwave Radiometer, is scheduled to launch somewhere around 2025, maybe a little later. It's in development with the European Space Agency. It is a microwave radiometer. So if you've dealt with sea surface temperature data, sea surface temperature comes in 2 forms. There is infrared sea surface temperature data, which is high resolution. It resolves small-scale eddies, and it doesn't work in cloudy conditions. So when David Marshall showed this amazing image of sea surface temperature in the Atlantic Ocean, and it was all beautiful and cloud-free and full of eddies. That's not the usual frame if you're trying to look at individual eddies. So if you want cloud-free data, we use microwave data, but microwave radiometers have typically had sort of a 50-kilometer resolution. What SIMR does is to put out a really big antenna, which reduces the resolution so that it gets about 15-kilometer resolution. And so that that will give, so it's got this structure like this, that'll give a much higher resolution sea surface temperature. And so that's a really nice way to, so that's what it's supposed to show, this rotating. That's a nice way to get the sea surface temperature that begins to give access towards looking at air-sea fluxes. But if you really want to measure fluxes, you need to have measurements in the atmospheric boundary layer as well to get the air-sea temperature and humidity difference. And so a few years ago, Butterfly was proposed to NASA. It did well, but it was not selected. But this is a concept that uses a microwave sounder to measure the temperature and humidity in the atmospheric boundary layer so that you can actually look at the fluxes across the air-sea difference, across the air-sea boundary. So it's using a whole bunch of microwave channels that make it possible to tell near-surface air temperature and humidity as well as surface temperature and wind speed. So this is something that is intended to be proposed again once the US finally offers an opportunity to propose it. It's like it could end up being teamed in some way with SIMR to take advantage of SIMR capabilities. So it's something where there's a prospect for actually being able to get measurements even in the Southern Ocean where it's always cloudy that would help with air-sea fluxes, at least in the twice-a-day sampling that we get from satellites. Then there's a question, what can we do about momentum exchange? And so that if you want to measure momentum transfer across the air-sea interface, you're really hoping to measure winds and surface currents in some meaningful way. So one strategy that is coming on board, if you want to do this at very small scales, comes from Harmony. Harmony is a SAR-based European mission which uses an existing satellite, a Sentinel SAR system that will measure 20-kilometer footprint patches of ocean, but then it flies 2 additional satellites so that you get 3 looks at the same patch of ocean. So there are 3 receivers for every pulsed radar signal. And that makes it possible to tell the wind with multiple looks, to tell the wind direction, the current direction, to tell something about waves, surface wave spectra. So it will provide really new information that make it possible to look at how the ocean and atmosphere are exchanging momentum in these small 20-kilometer by 20-kilometer vignettes. So it is an opportunity to get a sort of sub-mesoscale air-sea interaction. It is scheduled to launch in 2029. It doesn't really tackle global issues, but it's an opportunity that's worth thinking about how it will help the science that we would all like to do. On a different approach, Christine Goman-Ginger was the lead for a project proposed to ESA, Seastar, which was not selected. It has similar capabilities to Harmony. It's also but targeting coastal regions. So really trying to get this multiple looks from a SAR-based system at winds and currents and waves in a local area. And so that leads us to the question, what if you actually want to look globally, consistently, daily? And that's what Odyssey is proposed to do. So I'm serving as the PI for this. We just got word yesterday that we have been approved to move forward to the next stage. So we get a year of funding to write another proposal. It's very exciting and a lot of work ahead. But this is an instrument that will measure ocean winds and surface currents. It's essentially a scatterometer that also looks at the Doppler shift of the surface current so that it's possible to really tell how the winds and currents are interacting in a detailed way. It will give higher resolution than we've had in the past. So we'll go from being able to look at wind stress curl currently with this sort of resolution to something that really pulls into focus the details of wind stress curl across frontal features. And for surface currents, where we've had really limited observations, so we currently can reconstruct surface currents with a field like this, Odyssey will give us records that really pull into resolution the details of ocean surface currents in ways that will let us look much more closely at how the ocean is affecting momentum around. So just to summarize this graphically, if we want to look at turbulent heat fluxes, we need skin temperature, surface temperature of the ocean. Simmer is offering a great prospect for that. We need air temperature and humidity. Butterfly, if it's ever supported, will do that. And we need really good winds. Odyssey is one avenue that will help us with that. But ASCAT, COVR, and other missions are also providing. If we want to look at momentum exchange, depending on resolution, Odyssey gives the prospect of global measurements. C-STAR and Harmony will provide patchy measurements that look at small-scale processes. And if you want sea-state waves, then SCIM and C-STAR are really great quantities. So, and if we come back to this diagram, which is now in black, I guess we're in space, so we're looking at a dark sky, you can see how these lay out. So we looked at this range of scales at the beginning, and the different satellites have the prospect of capturing different parts of this spectrum. So Odyssey fills in this sort of large scale and time scales from annual to daily, winds and currents. Other missions will get different aspects of this. They have a very complementary role, and it's really important as a community that we look at the value in having a constellation of different satellites that will address some of our needs. So if you want to be part of this continued discussion, OASIS has served as a unifying framework for this. I mistyped that. Grand idea number 1, there is a distribution list webinar series for uncrewed surface vehicles. For grand idea number 2, for air-sea fluxes from space, we've been running webinars on Tuesdays at 8 a.m. Pacific time, 5 p.m. in Europe. You can sign up for these on the OASIS website. You can also find previous recordings on YouTube, and there's a large steering committee that's been keeping this going. So I invite any of you, if you're at all interested, to get involved, be part of the discussion. And some takeaways on air-sea fluxes. If we just wanted large-scale fluxes, that comes from the reservoirs, what's stored in the ocean, and that's our Argo campaign. But if we really want to understand the mechanisms that we need to understand fluxes, then we actually need measurements. And in situ observations in the Southern Ocean are sparse, but they're really sorely needed. Satellites we're at the cusp of having some really new opportunities. And then because I'm heavily invested in Odyssey, that needs to involve a community effort. And so I invite you all to be involved in this. There are opportunities to probe the science. If you're asking questions, to ask what types of measurements would do, and share that with us as we write our next proposal. And if you want to play with an Odyssey simulator, there's one online. You can play with it and try and imitate the data and see what it'll deliver. So I'm happy to take questions.